first half of our today, we're going to talk about localization. So remind some stuff and see how it relates to geometrical objects as we will now work. So we want to study rational functions f over g when f and g are two functions on some fine variety. Say fine. Okay, so it is hard to learn this globally because g is not they're not well defined. G have 0 somewhere. But what we can do is, if we want to restrict to a smaller neighborhood, then we can look at functions that do not vanish in this neighborhood. So, example 1, this is localization at a point. So take some point A in X and allow denominators G which do not vanish at A. Then f over G is a rational function defined on an arbitrarily small neighborhood of A. This is one example. This is the way that one should think about these functions. Another example is take some function f on x and restrict to this set by inverting all f squared, f triple, etc. So, well, we have seen stuff like this before when last was Friday. We had V which was r minus 0 inside one-dimensional R, and we built the structure of a variety on it by considering this set in the two-dimensional space. We basically forced y, which is 1 over x, to be invertible, or to exist. Okay? So basically inverted x squared, x cubed, etc. So now for proper definitions. So 1, f inside a ring R is multiplicative if 1 is inside, 0 is not inside, and if I have 2 elements inside, their product is inside. So this is a good set to be our denominators, and S inverse R is the ring of all fractions f over s, or r over s. S is in S. Sum and multiplication as you know from Russian numbers, but the equation is a bit different for some reason. This is true. Well, you would like to say this is true, but we actually want something a bit weaker. If there is some u in S such that u times r prime minus r prime is 0. So let's see why is this required geometrically. So, example. Take X to be the variety x, y equals to 0. Okay, so the proper ring R here is the ring of coordinates. It's just take xy over xy. So we want to localize this point, A, which is 1, 0. So at A, y and 0 are the same. So when localizing, we want that y over 1 would be the same as 0 over 1. So if we use the old definition, it translates to this equation, which is not true in our ring here. But if we take u, which is x, in the set S which we invert, basically functions with the not magnitude A, and we do have that this is 0. This is why we need this extra u. This from a geometric perspective. Okay, so the usual examples, as is S, which is what we invert, is one of two things. Either S is the complement of prime ideal, or that S is the powers of some n are non-element. Okay, so in the spirit of this example, exercise, maybe notation first before the exercise. If S is R equals P, the local S inverse R is denoted in this manner. The localization is P, and that if S is the powers of some element, then S inverse R is usually denoted R with subscript A. So, exercise. Let R be the ring KXY, XY. Show that the localization of R, the ideal generated by x minus 1 is isomorphic to kx localized at x minus 1. And explain this geometrically. What does this mean? And similarly, explain that why if I have this ring and localize it by the same ideal, we get this piece A. Any questions so far? Okay. So we talked today about a bit about open sets in affine varieties and closed sets in affine varieties. So suppose U inside X is affine is a principal open set, namely of the form F1 not 0, F2 not 0, Fm not 0. I can also write as F1 M not 0. Then I can give the structure U the structure from the affine variety by exactly localizing by set, then I exclude all the points which are not in U, and I get basically a structure of an affine variety in U. And well, if I have E inside S closed, inside U of the form G1 0 Gm prime 0, then E is a variety, is an affine variety. So basically, if I restrict the structure from U. So in general, not all open sets have the structure of affine varieties. For example, we gave an example today in lecture. This set not be affine, but it is true that these sets generate a topology, or form a basis of topology for the Zariski topology proposition. Principle of the set. From a basis of topology. So, proof. So, a general closed set F is basically the vanishing point of some L functions. So, U, which is its complement, is F1 non-zero, or F2 non-zero, or Fm non-zero, which is exactly the union from 1 to m F1 non-zero. Okay, and the intersection of two F1 non-zero intersection F2 non-zero is F1 times F2 non-zero. So this form a basis for the problem. Okay, so in particular, we can present locally closed sets using these. So make a definition just to make the words easier. A set inside X is good. This is of course not standard notation and terminology. If it is of the form F1 0, Fm 0, then G1 0, 0. The M prime 0. So plane, which is basically only trivial, the locally closed set, is the union of good sets. So why is that? If I'm taking a locally closed set C can be written as an open set intersection closed set, which is everything minus zeros of something. Intersection zeros of some other thing. And I can present them well basically the same way as theirs. F1 non zero and all of these are 0. And or F2 is 0 and all of these are 0s. And I think you see where this goes. This is a finite union. Forgot. Did I mention it? The finite union. Okay? So why is this important? Well, one reason is the following. I remind you that we did so in class, in that lecture, that if we have a morphism of affine varieties, then the image is constructible. So let me generalize this. Maybe I should. Oh, I said it out loud. Theorem. A morphism of affine varieties is constructible. So why is this? So maybe you call this morphism phi from x to y. So I take some C in X constructible, because C is the union of locally closed sets, and union is preserved under phi. It's enough to prove this for C which is not constructible, but locally closed. Because I can present such as finite union of locally closed. But actually, because what's written there, I can restrict myself to goods. See. Okay? Now, C has the structure of an affine variety, and I can look at the inclusion of C to X, which is a morphism, and I now have phi, which takes me to Y. So this is a morphism of affine varieties, meaning that phi of C is constructible. Or to be more rigorous, it's phi of the inclusion, which is phi of C. Okay? Any questions about that? So basically I reduce myself to sets which I know very well, and that's it. So seriously, any questions? Okay. So that's pretty much what I wanted to say about localization. And another thing that is explain something that was mentioned in class. Let's give an example. So we saw today that if G is an affine algebraic group, and H in G is normal, algebraic subgroup, affine algebraic subgroup, then G mod H is an affine group, affine algebraic group. So this is not so obvious. So, for example, if you take G, which is G to C, and H, which is the scalars, the G mod H is basically PGL to C, which is something which, at least in first sight, seems very far from affine. It's some open set in the projectivization of C4. It's quasi projective, but indeed it is affine. We're going to show that now. At least give a scheme of things. Well, shouldn't say scheme, but so the first thing that you should notice is that this group acts by linear transformations of something. On what to be exact? We have the action of G to C on 2x2 matrices over C by conjugation. And scalars act trivially, so this factors through PGL2. Each element here, each G PGL to C, isomorphism from PGL to C to GL4C, because the action is on something 4-dimensional over C. We want to understand this action, and basically what we'll show is that its image is an algebraic set. Because, well, the action is algebraic, so this is an algebraic morphism. And this will be an algebraic isomorphism PGL2 with some defined sum. Okay, so let's do this. So take a matrix A, B, C, D in, well, let me abuse the notation a bit. And this acts on a general 4-dimensional guy by conjugation. And let me not do the computation right now. Inverse, but it turns out that it is 1 over AB minus BC, AB times X minus AC times Y plus BD times Z minus BC times W. You have minus BA times X plus A squared times Y minus B squared times Z plus AB times W. Here you have CD times X minus C squared Y plus D squared Z minus CDW. And here you have minus BC X plus ACY minus BBZ plus ADW, sorry. So phi of this element is basically the matrix, can be seen as the matrix representing this in standard basis, which is this matrix, AD minus AC, BD minus BC, BA, C squared minus B squared, AB, CD minus C squared, D squared, CD squared, CD minus BC, AC minus BD, AB. So this is the general form of some element here. And let me, well, I work over C so I can just divide A, D, B, and C, the original matrix, by the square root of this. Make this just to swallow this already in the scalar A, D, B, and C. I'm allowed to because I work in PGL. So now comes the very technical part. One takes this general form of matrices and need to come up with many, many different polynomials, so that if some other matrix satisfies all of them, it must be of this form. So let's maybe try and see how such things should look. So let's maybe try to divide this matrix into 3 parts. It will be clear why later maybe. So if I know all of this, what's above this line, then it's easy to reconstruct those in some sense. Why? This is the same as this, which is one polynomial. This is the same as this, after sign. This is the same as this, with a minus. This is the same as this, etc. So if we know all above this line, we can reconstruct the bottom. Or if we found AB which works, this must be the form. Now this part is a bit trickier. Why is that? Well, you would like to say, for example, AC times BC is minus BC minus BC, BA, sorry, minus C squared.
What are you doing now?
I'm trying to explain how to build more polynomials that these matrices satisfy, which will be enough to ensure that any matrix that satisfies them is of this form.
So basically you're proving that the image is closed?
Yes. Well, sorry. This is very interesting, but it's done, I think. Then you have, for example, this identity, which basically means that this times this is minus, sorry, is this times this, not minus it. Which is one example, which gives you c squared if you know all of these, but only provided that this product is not zero, or that this is not zero, for example. Sorry, this is not zero, this is what I wanted to say. So now you see that we need to divide into cases in order to, or not really divide into cases, but because you can't, but just write many polynomials, so that no matter in which state do we fall, we can always reconstruct stuff.
But doesn't it follow that the image is closed from some general things? Like we can present this image as as the image of morphism from space about which we know that it's an algebraic group, right? From just from GL and not DGL.
Okay.
Too. And then we know that.
So this is the image in.
Okay, so this is morphism of algebraic groups. Okay, to GL for.
Yes, this is the morphism of algebra.
So the image is.
Okay, this is way easier.
Close, right? So this.
Yeah.
Okay, we didn't prove it, but
We did. We pulled the image of the.
yeah, prove so.
Oh, so yeah, so you can say that this is easier, way easier. But okay. So let me just okay, so okay, so maybe I should say something. I did wanted to give maybe a more elementary proof without using this, but this is much simpler, so I will drop this out. But yeah, now you can see that the image is closed, which is enough. Okay, so
Why the image is closed?
it's a morphism between affine varieties and
To algebraic groups.
algebraic groups even, yes.
So the image is a constructible.
Yeah.
So it has to be closed.
It has to be locally closed.
No, I have a constructible subgroup of algebraic group which is closed.
Why?
Well, okay, as you said, it's locally closed, but why multiple exactly closed? No, sorry. Yeah, well, the complement is homogeneous as well, so if it's non-empty, then it has to have non-empty interior, so the complement is open.
Exactly. Okay. So let me abandon this huge computational stuff and do something else. Or maybe present something if there are no questions.
If the complementary has no empty interior, it doesn't mean that. It's a lot, but fine.
Yeah, but still true. But
So you want to show the image is closed, I think you need to have two steps. First it is constructible, then you show it is locally closed, you have to argue here somehow. And then if it is locally closed, then it is actually closed.
Because I don't see the last step.
not sorry.
I mean, fair not to answer.
But, maybe.
So we did see that the image is constructible. This is a general fact about morphisms. A constructible set contains an open set, and indeed, as was argued here,
So thank you. So let me, if there are no other questions, maybe start something else, put some definitions on the board for tomorrow. If there are no questions. Okay, so in class we said that we can work on fields which fields K which are complete with respect algebraically closed and complete with absolute value. So one question that one can ask is, what absolute values are there on fields? So there are many examples. So you can take R with the usual absolute value that you know, like this, and similarly C with it, Q with it. And you can take, for example, Q with the p-adic absolute value is prime. So if you have something of this form, when M is an integer and A and B are prime to P, this is that P2 minus M. And if you know what are these, then you have the p-adics, which extended. You have more examples. So maybe an abstract definition on what absolute value is. Let me do it there. So definition. K field. An absolute value K is is a map from K to non-negative numbers such that at first you have that x is 0 if and only if x is a 0 point. This is basically the axioms of multiplicity, something like a multiplicative norm or something. You want this to be multiplicative, and you want the triangular inequality. So this has a stronger version. So K with this absolute value is non-Archimedean if we have 3 prime, and x plus y is bounded by the maximum of x and y. Okay, so what we're going to do tomorrow is to classify all absolute values, say, for stars and Q, and then basically, how do you say? Basically classify all absolute values which are Archimedean at all. Okay, then the field is complete with respect to them. So let me maybe put a lemma for next time. So this is an absolute value. Then the following are equivalent. One is that for every n, in n, the absolute value of n is bounded by 1. And 2 is that this is non-Archimedean, meaning that you can see being non-Archimedean only by looking at these elements. So the proof, this direction is easy. Basically, the absolute value of n is the absolute value of summing 1 n times is bounded by the maximum such. And well, one can see by this and this implication that the absolute value of 1 is 1.
So it's also the absolute value on any field?
You can, but mostly, sometimes it's not that interesting.
In this lemma,
In this lemma, yes, the absolute values are arbitrary,
so
and this is defined as 1 plus 1 plus,
okay,
plus 1 n times.
okay.
Okay? So this is one direction. The other direction goes as follows. So take x and y in k.
Maybe I should make
Sure, go ahead.
an exercise. Show that if you have an absent value, not regular absent value in the field, then the characteristic is zero. Oh, sorry. Okay.
Okay, so let me go back to this. We now assume that the absolute value of all.
I meant the median.
Yes. This basically shows this for one example, for one way. So take two elements of the field. And what we do in order to estimate this, we're going to look instead on this. So by binomial identity, we can write this in this manner. Triangle inequality and then multiplicativeness gives me this. This is bounded by 1 because this is some integer. This is bounded to n, x to the power I to the power n minus I. And this can be bounded by number of summons, n plus 1, times the maximum, the absolute value of x, absolute value of y. Say 1 just to make sure if both of them are less than 1, power n. Oh, sorry, don't even need this. Now if I take nth root, like doing nothing here, then n, so this goes 1 over n, and this vanishes. This goes n goes to infinity. X and y. Okay, so this shows that you can view being an Archimedean basically by looking at the integers themselves. And let me stop for today. So maybe before I stop for today, just to make you hungry for tomorrow. So the first theorem that I'm going to prove, theorem by Ostrovsky, says that if this is an absolute value on Q, then it's either, well, the normal absolute value that the Euclidean absolute value, a p-adic absolute value, prime, or something stupid, which is the trivial one, basically gives the value, the absolute value of x to be either 1 or 0, and it's 0 if f equals to 0. This is a stupid one. Well, this can't be true, because if you have an absolute value, you can take the square root of it and it still works. So in general, what you have here is that you need to put some power here, and in order for the axioms to be satisfied, alpha needs to be somewhere between 1 and 0. So this is what I'm going to prove tomorrow. One of the things that I'm going to prove tomorrow. Okay, thank you.
In the second case, alpha would be alpha.
Yes. So yes, you should mention thank you. Okay, so So maybe just a counter remark. In general, if you have an absolute value, you can only assure that for these values of alpha, its power will be an absolute value. But here, because what happens in the background is that you have a valuation, you can actually take these values of alpha. So now you can confirm after cutting this 3 times. Thanks, and see you tomorrow.